Welcome to this explainer. Today, we're going to completely demystify the microscopic world. We'll trace a truly fascinating journey that kicks off with ancient philosophy and ends with the modern secret code of the elements, the very stuff that makes up, well, everything around us. It's an incredible story full of shattered illusions, brilliant experiments, and absolutely mind-boggling scale.
Here's our roadmap for today. First, Dalton's atomic foundation. Second, discovering subatomic particles. Third, the Rutherford revolution. Fourth, anatomy of the atom. And finally, 5, isotopes, ions, and symbols. Let's get right into it.
Section 1, Dalton's atomic foundation. Let's start with Act 1 of our detective story, how we used to think matter was built, and the guy who laid the groundwork for modern chemistry.
Okay, let's dive into this. To really appreciate atomic theory, you first have to wrap your head around the sheer, unfathomable scale of atoms. Think about a standard pre-1982 copper penny. And I say pre-1982 because modern pennies are actually mostly zinc. Now, it feels completely solid, right? But it actually contains approximately 3 × 10 to the 22nd power identical copper atoms. That is literally a 3 followed by 22 zeros. A macroscopic sample of an element contains just an incredibly massive number of atoms, and every single one of those copper atoms has the exact same chemical properties.
So the man who first put this all into a cohesive scientific framework was an English schoolteacher named John Dalton. Published way back in 1807, his atomic theory had a few core postulates. He stated that matter is composed of exceedingly small, indivisible particles called atoms. An element consists of only one type of atom, and atoms of one element differ from all other elements. He also figured out that a compound is just a combination of these atoms in small whole number ratios. That specific idea cemented what we call the laws of definite and multiple proportions. And finally, atoms are neither created nor destroyed during a chemical change, they literally just rearrange themselves. At the time, Dalton basically pictured the atom as a solid, indestructible sphere, like a tiny billiard ball.
What's really wild about this timeline is just how long it took us to get to Dalton in the first place. In the 5th century BC, ancient Greek philosophers Leucippus and Democritus proposed the concept of atomos, which means indivisible. But then Aristotle came along. He argued that matter was just earth, air, fire, and water and could be infinitely divided. And crazily enough, that Aristotelian view basically stalled scientific progress for over 2,000 years. It wasn't until Dalton in 1807 that atoms finally moved from a purely philosophical concept to a testable scientific theory. And from there, the science evolved incredibly fast.
Section 2, Discovering subatomic particles. This brings us to a major turning point, where Dalton's idea of the solid, indivisible atom gets completely turned on its head.
This was the exact mystery scientists faced in the late 1800s. I want you to just think about this question for a second. If matter is composed of atoms, what are atoms composed of? Are they truly the absolute smallest particles in the universe, or is there something hiding inside them?
Well, English physicist J.J. Thomson answered this using something called a cathode ray tube. He took a sealed glass tube, sucked out almost all the air, and applied a massive high voltage right across 2 metal electrodes. This created a glowing visible beam. But here is the absolutely crucial part. This beam was deflected toward a positive charge and pushed away from a negative charge. By measuring those deflections, Thomson calculated that whatever these particles were, they were much, much lighter than atoms. He had discovered the electron, a tiny, negatively charged subatomic particle. Shortly after that, Robert Millikan used falling oil drops to determine the electron's exact charge and mass. So Dalton's solid sphere model? Officially dead. The atom had parts.
Section 3, The Rutherford revolution. Thomson's discovery created a totally new problem. If atoms contain negative electrons, but atoms themselves are electrically neutral, where is the positive charge hiding?
Enter Ernest Rutherford and his colleagues in 1911. They designed this utterly brilliant experiment where they fired a beam of high-speed, positively charged alpha particles directly at a super thin piece of gold foil. Now, they fully expected these heavy alpha particles to basically punch right through the diffuse soup of positive charge, maybe deflecting just a tiny, tiny bit. They set up a luminescent screen all around it to see exactly where the particles landed after hitting the gold.
But the results completely shocking. While most particles did pass straight through just like they expected, a very small number were deflected at massive angles. Some of them even bounced straight back, literally bouncing off the foil. So the crucial point is Rutherford's groundbreaking conclusion. The volume occupied by an atom must consist of a large amount of empty space. The positive charge wasn't spread out evenly at all. It was intensely concentrated in a tiny, incredibly dense, positively charged body right at the very center, which he named the nucleus.
Section 4. Anatomy of the atom. So, let's pivot away from our historical detective story for a minute and look at the final, assembled modern atomic model.
And this brilliantly illustrates exactly what Rutherford discovered about empty space. The diameter of an atom is about 100,000 times larger than the diameter of its nucleus. Let's put that into perspective. If you could somehow expand a single atom to the size of a massive professional football stadium, the nucleus, which contains almost all of the atom's actual mass, would be the size of a single blueberry sitting right there on the 50-yard line. The rest of the stadium? That's just the vast, empty space where those tiny electrons orbit. Kind of blows your mind, doesn't it?
Let's synthesize all of this into a clean user's manual. The atom is made of three fundamental subatomic particles. The electron, located out in that vast space outside the nucleus, has a -1 charge and practically zero mass. Inside our blueberry nucleus, we have protons, which have a +1 charge and a mass of about 1 atomic mass unit. And joining those protons in the nucleus are neutrons. Neutrons are just slightly heavier than protons, but they carry absolutely zero electrical charge. They're completely neutral. The specific number of protons determines the atomic number, which is the magic number that tells you exactly what element you're looking at.
Section 5. Isotopes, ions, and symbols. Now that we've got the anatomy down, let's move to our final section and learn how chemists use this knowledge to read the secret code of the elements.
Back in the early 1900s, English chemist Frederick Soddy won a Nobel Prize for a really fascinating realization. He figured out that you can have atoms of the exact same element that are chemically indistinguishable, but they actually have different weights. We call these isotopes. Because the number of protons defines what the element is, that number can never, ever change, but the number of neutrons in the nucleus, that can change, which alters the atom's total mass without changing its core chemical identity.
Now, what's really interesting about this secret code is how chemists write all of this information down into a single compact symbol. Take the notation for magnesium, usually written as Mg. You'll typically see a number on the bottom left. That's the atomic number, 12 in this case. That means 12 protons. The number on the top left is the mass number. Let's say 24. The mass number is the total number of protons plus neutrons. So 24 minus 12 means this specific isotope has 12 neutrons. Sometimes that atomic number at the bottom is just left off entirely, simply because the symbol Mg already tells any chemist that it definitely has 12 protons. Finally, the top right corner shows the electrical charge. If you see a 2+ up there, you know it's not neutral.
But wait, how does an atom even get a 2+ charge? Normally, atoms are naturally electrically neutral. They have the exact same number of positive protons and negative electrons. But they can gain or lose those lightweight electrons orbiting around the outside. If an atom loses electrons, it loses some of its negative charge, leaving it positively charged overall. We call that a cation. Conversely, if an atom gains extra electrons, it becomes a negatively charged ion, and we call that an anion.
Now, if you're sitting there wondering why any of this matters in the real world, just look at your kitchen table. Iodine is an essential trace element our bodies desperately need to produce thyroid hormone. Without it, you can develop a goiter, which is this severe, really uncomfortable enlargement of the thyroid gland. To prevent this, public health officials started adding small amounts of iodine to regular table salt, which practically wiped out the disease in the US. But here's the catch. They don't add neutral iodine atoms. They add iodine anions, atoms that have actively gained an extra electron, giving them a -1 charge. That tiny subatomic change makes the iodine stable enough to just sit harmlessly right there in your salt shaker.
So we've gone from Dalton's solid, billiard ball spheres all the way to Rutherford's vast empty stadiums, which leaves me with a final, pretty deep question for you to ponder. If literally everything you interact with, the chair you're sitting on, the screen you're looking at, your own body, is made of atoms, and we know that atoms are mostly empty space, what does that say about the physical world around you? Are the solid objects you touch every single day truly solid? I'm going to leave you with that staggering thought. Thanks so much for joining me on this explainer to explore the evolution of atomic theory, and hey, keep questioning the world around you.